The model is also adaptive. The avatars in the model, we don't necessarily know what they're going to do. We don't pre-program them necessarily to go down a particular route. They adapt their behavior, and at the end of the day, they may change where they want to go, depending on the situation that they find themselves in. So the model is adaptive. Here we have an example of a visibility catchment area. Here we have a sign above a door, and what's shaded in green is what we've termed the visibility catchment area. Where is it physically possible to see this sign from? Now this sign has got characteristics, it's got a certain size, and it's got a certain height. These obstacles in the way have certain heights, and what we're calculating here is for a particular height occupant, where could they possibly see that sign from? The visibility catchment area of that sign. The visibility catchment area, as I said, takes a number of factors into account. Takes the height of the observer, the height of the obstacle, where the sign is, the size of the sign, the height of the sign, and so on. And we have a termination distance for the visibility catchment area. At the moment, that's based on what's written in the regulations. So you can't see the sign indefinitely in a straight line. There'll be a termination distance based on the size of the sign and the size of the lettering. And we also have an angle of view. You can't see the sign if you're looking parallel along the sign. So there's an angle of view built into the visibility catchment area as well. One of the things about visibility catchment areas is that this shadow area where the sign is not visible from can take on very complex shapes. And in fact, you can get islands of visibility in a sea of invisibility. So the visibility catchment area becomes a very complex structured entity. The other thing that we've built into it is it's not simply if you're in the visibility catchment area and you're looking at the sign, you could be in the visibility catchment area and so it's physically possible to see the sign, but my back might be to it. And so what we've done is we've taken into account the direction vector of the person, the direction in which they're moving, to the normal vector of the sign. And we calculate the angle between them and we give a probability that you'll actually see the sign based on that angle. And at the moment, this is the probability distribution we're using. So basically, if you're 180 degrees to the sign, you're not going to see it. You've got a very minimal probability, and the distribution varies as follows. Now, this is based on, if you like, informed engineering judgment as to what this distribution is likely to be. We're in the process of measuring this with several hundred people in various situations and so on. So we hopefully will be able to build a proper probability distribution function based on experience of observers. So what we've talked about thus far is the ability to physically see the sign. You now have the recognition, interpretation, and action components, the behavioral components of this interaction of signage. Now, again, we're doing some experiments where we're attaching video cameras to people's heads, and we're putting them in various situations, and we're recording what they do when they see signs. But at the moment, in the software, we don't have enough data to put firm numbers on this. It's a number that the engineer can dial up. You can say that, for example, you'll have 100% interpretation, recognition, and so on, or you've got 5% interpretation, recognition, and so on. But in the calculations I'm going to show you here, we're looking at it very optimistically, and we're saying you've got 100% chance of picking up the sign. Now here's an example. This is our local supermarket, Sainsbury's Supermarket, which is supposed to be the flagship Sainsbury's store in the country. It's up the road here in Greenwich. And what we did was, I think it's quite awful in that store. You can't see where the emergency exits are at all anywhere. And so I decided we'd actually model this and see what it actually looks like. We've put in the exit signs that exist around on all the exits. We've got the heights of all the obstacles in the store. There are basically 4 normal exits at the front and 4 emergency exits around the periphery. Here you can see an example of the visibility catchment area being calculated for a sign above one of the doors. And here you can see we've actually added in a number of additional signs. These signs don't exist in the actual store. We've just added in 4 extra signs to see what impact this might have. This is the height of all the obstacles. The main shelving is about 2.5 meters high. These shelving are about 1.2 meters and so on. Now here are the visibility catchment areas that we've calculated. This is based on the existing signage in the store. And as you can see, it's physically possible to see an exit sign from 53% of the floor area. But there are vast regions in which you can't see a sign to an exit at all. With these additional signs we've placed in these areas, this is the additional visibility catchment area. It gives you 32% coverage, these additional signs we've put in. And if you combine our suggested signs with the existing signs, you see you get a 69% coverage. Now, we can put in a few more signs to improve this, but that wasn't the purpose of this exercise. It was really just to demonstrate the visibility catchment area concept. But, oops. Now, we're going to run a simulation. We're going to put 1,000 people in this store. We're going to give them instant response time, so we're not trying to measure real response times here or represent real response times. We're going to make all the occupants only aware of initially the main entrance and exits, where they've come in through, basically. And they don't know about the other exits. And we're going to give them, but we're also going to give them 100% recognition. If they see a sign, they will follow it. The occupants will also elect to go to their nearest exit. So if they're heading to an exit that they know exists, and the sign is saying, well, hang on, there's another exit over there, the occupant will make a decision, and the decision he's going to make is, well, okay, I know that exists, but I'm going to go to my nearest exit. So they're making that judgment. Here you'll see one simulation where we're giving the people this recognition, and you can see the people flocking to these emergency exits. This is a view from the height of an observer flying through the geometry, and you can see the situation where the people are below the shelving and they can't really see the normal signage above the exits. This is one of the additional signs we've added into the simulation. But you can see that we get a good distribution of people going to the emergency exits. And this is not the case if there's no signage system as we've identified. If you just look at the evacuation times, if you have this 100% follow-up on the signage system, then the evacuation time is about 1 minute 23 seconds compared to 3 minutes and 2 seconds when the occupants don't follow the signage. And you can also see the reduction in travel distance if they follow the emergency signage, 28.7 meters compared to 42.5. Here are some of the example paths that some of the occupants have followed. Now this chap who started off here, he's heading towards this exit, and even though he's passed this region here where he can see the sign, the probability distribution said he didn't see it. And so he just ignored the signage, even though that exit there would have been closer. He just continued on because he didn't see the sign. This chap over here was heading off to go to the exit that he knows about, but as he reached this point here, he saw the sign there that was directing him to an exit back here, and he decided to take that path. Similarly with some of these people here, you can see that they've changed the direction that they've followed because they've intersected this visibility catchment area. Here we're going to zoom in and see some of that actual behavior taking place. This occupant here in red, she's heading off. She can't see a sign at the moment. She's just turned the corner, and now she's actually heading to the main exit. But she's seen a sign on the side here which has directed her that there's an exit just to her side. This is another occupant coming out. Again, she's heading towards the front exit, but she's seen the sign here which is directing her to an exit behind her, and she's picking up on that and following that. Now, in these simulations, we've used 100% recognition. Now, we've also run cases where you've got 10% recognition, and you obviously see a different set of results. But you can see the impact that the signage system could have if people actually were able to detect the sign and were prepared to follow it. And you can see why it's important to have this sort of information, this capability, in your evacuation simulation, and also your circulation simulation, not just for evacuation. This is showing the case where the VCA is enabled. It's showing you the footfall of the occupants, the paths the occupants taking to use this exit. And this is the case where the VCA is disabled. And you can see here